Hello there. So in the last video, we talked about how the cells of the SA node are able to spontaneously generate an action potential because they have this leaky sodium channel. And we also talked about how when a cardiac myocyte depolarizes, it depolarizes all the other myocytes it's connected to because they're all connected through gap junctions, which allow the action potential to go directly from one cell to the next. So what I want to talk about in this video is the path that depolarization takes through the heart every time in a healthy heart. And how we measure that is something that's called the EKG or the ECG, which stands for electrocardiogram. K if you're German, where this was invented, and C if you're American or English speaking. I don't know. Anyway, let's first talk about the pathway. So the depolarization, which begins in the SA node, always follows a very predictable specific pathway in the healthy heart. We start with the SA node, which is pictured right here. And after the SA node fires, the action potential that it creates goes through the gap junctions to the cells that are just outside it. And it starts to spread outward like a ripple from a drop in the pond. So we see this next step is that the depolarization is spreading through the atria. Now, you might be wondering why the depolarization doesn't go all the way down to the ventricles at this point, but it's because there is a barrier between the atria and the ventricles which prevents depolarization from going from one cell to the next. So the atria and the ventricles have to be depolarized separately, sort of. Now, there is one place for the signal to get from the atria to the ventricles, and that's through this structure, which is the AV node. Now, as the signal travels through this AV node, it gets really slow, way slower than anywhere else in the pathway. And the reason for this is that at the point that the signal is reaching the AV node from the atria are just beginning to contract and push that last bit of blood into the ventricles. We don't want the ventricles to contract at the exact same time. It would push the blood back into the atria or prevent the ventricles from filling all the way. So by having the signal delayed here, we allow enough time for the atria to depolarize and contract and fill those ventricles completely with blood. Now, about the time that the atria are starting to contract, the signal gets out of the AV node and it rockets over to the interventricular septum, or the wall between the ventricles. This little spot is called the AV bundle, or sometimes referred to as the bundle of His. And so it zips over to get between the ventricles and then branches into the right and left bundle branches. Now, all of these, let's call them wires for lack of a better term, are like insulated wires, which means that the depolarization is traveling along and it's not spreading to the myocytes that the wire is traveling through. But once the bundle branches reach the apex of the heart, or slightly higher up in a couple of other places, it turns into these thinner fibers, which are called Purkinje fibers. I forgot to click the thing here. Okay, so AV bundles and bundle branches to reach the apex, and now we have our Purkinje fibers. The Purkinje fibers are like our wires, but they're not insulated, which means as soon as the depolarization arrives at the Purkinje fiber, it spreads to the cardiac myocytes that are next to it, and then to the ones that are next to them, again, like a ripple spreading in a pond. So what that means is that when the atria depolarize, they sort of start from the top and depolarize going down, which means the contraction starts from the top and pushes down. which is what we want because we want the blood to go from the atria to the ventricles. But with the ventricles, the depolarization starts at the apex or the bottom and it spreads upwards, which means contraction starts at the bottom and spreads upwards. And because it's spiral, it's like wringing the blood out of the ventricles and pushing it up into the great arteries. So the path of depolarization is also the path of contraction, and the way that the depolarization pathway is structured allows for the most efficient movement of blood in the heart. Okay, so how do we know what this path is, and how do we know when it's not working in someone? Well, the EKG was invented as a way to see, in quotes, the electrical pathway as it spreads. So if you imagine, instead of depolarization, which means nothing to us, that we're talking about a light spreading through the walls of the heart, then that is what the EKG is showing us. Where is that light going? Only it's tracing it in a little line that we have to learn to interpret. Now, in an EKG, there are several leads that are attached to different parts of the patient's chest. And then there are other parts further away on the body. And the EKG is comparing the electrical signal between every pair of these electrodes. And this gives a picture of what the path of light or depolarization looks like from that particular angle. Now, that means that when you read an actual EKG, there are lots of different proper ways for it to look from that angle. We're going to take a look at the EKG straight on from the center of the chest, which is right here. And this is what a typical reading from that lead looks like. However, if you're really going to diagnose a patient, you have to be able to look from the top, look from the bottom, look from the left, from the right, all kinds of different angles to see if that path of depolarization is not moving in the right direction or the right way. Okay, so let's look at this typical EKG reading. Each deflection in this line indicates that there's a movement of depolarization, and they're named according to letters of the alphabet for some reason, starting with, which I didn't put up here, P. P, Q, R, S, T. All right, so they don't stand for anything, but they're just sequential letters in the alphabet. Okay, so let's look at what this diagram means. So initially, before there's anything, this flat line means that there's no significant depolarization. There's nothing big enough, no light being emitted that's bright enough to be picked up. And that's because the heart right now is relaxing. Now, remember the SA nodes start this off and depolarize, and that starts to spread through the atria. So we can't see the SA node. There's not enough cells there doing this to actually emit light that we can detect or depolarization we can detect. But when it starts to spread through the atria, we start to see something. We start to sense something. But we know that the SA node had to fire here or else we would not have this deflection. This is called the P wave, and this is what we see when the depolarization is spreading through the atria. Okay, so now that the depolarization has spread through the atria start to contract. We can't see that on the EKG, we just know that it's happening. And as the atria are contracting, the signal is trapped or stuck in traffic at, whoops, I didn't label it, at the AV node. Right, so we're delayed in traffic here. That's this straight line. So this little line between the P wave and what comes next is the delay in the AV node that allows the ventricles time to fill. Okay, as soon as we get through the AV node, the depolarization shoots across to the interventricular septum through the bundle of his, or the AV bundle, and that's this small little downward deflection that's labeled Q. Then it very quickly moves through the bundle branches, moves through the bundle branches towards the apex. That's this deflection, R. As the depolarization starts to move from the apex back up towards the ventricular, towards the base, towards the top of the ventricles, then we see this deflection down to S. This is also when we start to see the contraction at the apex of the ventricles moving up and twisting as it moves up the ventricles. Now, remember how the ventricles have this special action potential that creates a plateau where it can squeeze and hold to get the most blood out? That's what we see here just after the S. Nothing else is happening. There's no depolarization spreading, so the machine can't pick anything up. But because the calcium is still there in the cells are contracting and holding that contraction. Okay, so the cells begin to recover. They reach the end of their action potential and they repolarize and they start to relax. As they repolarize, we see the T wave as a deflection appear on the EKG. So that's where the repolarization starts to move from the bottom to the top. You may be wondering, well, when did the atria repolarize? We sort of skipped over that. And we did. The atria repolarize here underneath the QRS complex. But because the ventricles are so much bigger, when they depolarize, they produce so much more signal, it overrides anything we might see from just the atria. Okay, and when the ventricles are fully repolarized and we're just resting before the next heartbeat begins, we go back to this flat line. Okay, so looking again at the parts of the EKG, the heart is at rest. The SA node fires here, which we can't see, but we know that it did because we see the P wave, which is where the atria are depolarizing. It's spreading through the atria. Now it's stuck in the AV node while the atria are contracting. We can't see the contraction on here, but we can see that there's not much traffic moving because we've got a flat line. Now, all of a sudden, we see a quick dip and a rapid rise and another dip, the QRS complex. That means that we've just gotten out of the AV node. We're going through the bundle, the AV bundle, through the bundle branches, and then up through the Purkinje fibers, which means the ventricles are beginning to contract now. Those ventricles contract and hold their contractions, so that's a long action potential. And when the cells finally begin to repolarize and relax, we see the T wave at the end of that reading. And after everything's repolarized, we get a little break before it starts again. The faster your heart is beating, the shorter this segment between the beginning and end of each EKG. These don't get that much closer together. So it's mainly the gap between the beats that speeds up when your heart rate does. Okay, so let's take a look at some EKGs and see if we can diagnose our patients. At the top, in each case, I've got a normal EKG, and at the bottom, I've got one that I want us to diagnose. So take a moment. Here you can see the P, QRS, T. And in the bottom, there's no P, QRS, and then T. So there's no P wave. Now, if there's no P wave, that means that the SA node didn't fire. Right, so the SA node didn't fire and the atria are not depolarizing. Lucky for us, remember there's a backup. The AV node is able to initiate a heartbeat. So the AV node is actually kicking things off, and we're just pretending like the atria don't exist. So this is when the SA node is not working and the atria don't depolarize. It's not very obvious on this diagram, but these should also be further apart in this case because the AV node has a slower heart rate somewhat than the SA node. Okay, again, we've got our normal EKG at the top, and then something wonky happens in the bottom EKG. So we've got P, QRS, T, and then let, and then the QRS goes the other way, and then I guess this is a crazy T, and I don't know what's going on here. So what's happening here is that on most heartbeats, it's normal. We've got the SA node kicking things off, the atria depolarize, the ventricles depolarize, the ventricles repolarize. But what's happening here is we're missing the P wave and the QRS is going in the wrong direction. So that means that the depolarization didn't start at the AV node and then go across and down and back up, because that gives us this shape. It took a different path altogether without a P wave. So this means that the ventricular myocytes decided to initiate a heartbeat all on their own without asking the SA node or the AV node to do it first, even though they were working just fine. So this is called a premature ventricular contraction. And it happens when we have high anxiety. And this is because we have the parasympathetic and the sympathetic nervous system sending signals to the heart to speed up the heart rate or slow the heart rate down. Now, the parasympathetic only talks to the big bosses. It's like SA node, just instead of being at this heart rate, slow it down, conserve some energy. AV node, same thing. Just, bring it down a notch and let's save some energy. But it doesn't talk to the myocytes themselves. However, the sympathetic, the fight or flight, which is our danger nervous system, has a way to talk to the SA node. And it's like, hey, tell them to speed up. Talks to the AV node, hey, tell them to speed up. And because we can't entirely trust them to pass the message on, it goes right to the ventricular myocytes and says, guys, speed up. It's a matter of life or death. So the ventricular myocytes are like, okay, let's start a heartbeat right now. It's an emergency. And so they begin the signal, and instead of it traveling the normal pathway, it starts in the ventricles, and the contraction, therefore, isn't as coordinated either. We sometimes experience this as a missed beat or just something like a flutter in the heart almost. Okay, next one. We've got a normal one at the top. We've got a normal heartbeat here, and then here we've got a P wave and nothing. A P wave and then nothing. So the P wave tells us the SA node fired, the atria depolarized, but somewhere here we got stuck in the AV node and we never came out. So what's happening here is that we've got a block in the AV node, also known as heart block. And so what will happen is that every once in a while it might get through until the block is complete. But here it's just the atria contracting. Now, if this lasts for very long, then the AV node should pick up and start initiating the heartbeats or the ventricular myocytes. But when we see this missing, we know that there's a blockage in the AV node. All right, last one. What's going on here? All right, so there's no real pattern, right? It's just a random squiggly line. But the good news is that it's a random squiggly line. If it were a flat line, then we'd be in even bigger trouble because flat lines do not mean good things in biology. All right, so we've got no pattern here. And what that means is that the depolarization isn't following that standard path, it's zigzagging all over the place. So if it were light, it would be less like a what do you call it, a bolt of lightning, and more like a firefly moving around. This is called ventricular fibrillation. And what's happening here is exactly that. Something's wrong with the system that usually allows the depolarization to spread in a predictable way. And now it's going this way and that way. And because cells have had a chance to rest, they'll contract again. If you're looking at the outside of this heart, it looks almost like a bag of worms. The contractions are not coordinated at all. And if it's not coordinated, it's not pumping out blood. For this particular condition, we use something called a defibrillator, and there are modern ones that anyone can use that are automated AEDs that we see around. This is kind of an old-fashioned one that you'd see in the emergency room. But the idea is that we apply a shock to the body that causes all of the heart muscle cells to depolarize, right? Actually, it will be all of the muscle cells. So when a muscle cell depolarizes, it contracts. So if we could see the heart at that moment, the heart would seize up. But also, if you look at the person's body, their muscles will contract. So everything's depolarizing and contracting. And after that, everything should start to repolarize and relax. And the hope is that in that moment that there's quiet, there's not signals still bouncing around in the ventricles, the SA node can initiate a new action potential and start the heartbeat over again in a predictable way. Now, this does not fix the problem permanently, but it keeps the person alive until we get them to the emergency room where we can do some more investigating and hopefully fix the problem. All right.